Hello, my name is Tai and I'm a graduate student at UCI, majoring in mechanical engineering. Our design project consists of prototyping a wearable device to help capture continuous blood pressure on the radial artery. This team consists of 5 graduate student engineers, Pardis and Evan, who are both biomedical, Rebecca, who's mechanical, and Kyra and Mara, who are also both biomedical engineers.
These are the parameters which help lead in the development of our prototype devices. Weighted by importance, the various metrics with which we grade ideas and prototypes are shown in this pew chart. When brainstorming, each idea is scored on each of these weighted criteria and total scores are calculated. Finally, the top 2 designs are pursued. After prototyping these 2 designs, the prototypes are also tested and graded based on these design requirements.
The brainstorming conducted by the team led to different design concepts that we divided into 3 categories based on their working principle. We had 2 designs that work by changing pressure with air, 2 designs that work with kinetic systems, and finally, some designs based on the smart material properties to create a planation. For this last category, after doing extensive research, we found that we needed much more knowledge on material science to almost create our own material.
Inspiration for our first device came when observing cardiac procedures. After catheter removal from the radial artery, a device called the TR band was used to apply pressure and stop the bleeding. We adapted this existing device to our use case.
Design 2 is inspired by the well-known wrist blood pressure monitor. The idea is to use an air pump to inflate a sigma cuff. Design 2.1 is a cuff that inflates around the wrist, and Design 2.2 is a glove with an air pump at the wrist level.
The third design consists of a manual tightening system that includes a Velcro band attached to an acrylic backing with a screw. It applies pressure to the radial artery by manually moving the screw to pull and fasten the 2 acrylic discs.
Design 4 incorporates a similar mechanism as in Design 3. However, we will have a motor controlling that tightening mechanism. Note that when I say tighten, it relates directly with pressure. The motor will be controlled remotely via an app or software. This design will ideally be a 2-band design, one for the sensor and the other for the motor.
Design 5 is an ergonomic design that fits all. It's made of adjustable, elastic, self-adhesive gel with embedded VV sensor, which pastes firmly on the wrist. This has enough elasticity to increase the pressure needed to acquire a good signal.
We use put chart to down-select the 5 designs mentioned before by scoring each of them based on their performance in each design requirement. To its highest total score, which is number 2, automatic air pump design, and number 4, kinetic motor design, is what we want to pursue. As these 2 designs achieve the highest performance when holding a constant pressure for a stable reading in the desired bore measurement range during a whole experiment, and also because they are more robust and user-friendly comparing to the other 3.
The kinetic motor design is based off of the bike fit helmet system using rack and pinion mechanics. The tightening and loosening controls are made via a stepper motor. The videos shown here demonstrates the components and how it works. Unfortunately, due to time constraints, we were not able to pursue this design.
This is the final design of our product, a wearable device that applies pressure on the radial artery by using an automatic air pump. The goal was to create a user-friendly, small and adjustable wearable for the wrist, and we wanted it to be interactive and controlled by the end user. It has 8 main components, including the display, electronics, pump and tubing system, battery case, adjustable band, and the pressure cuff with an embedded sensor. As you can see on the images, once the user starts the blood pressure monitoring on the device, the automatic air pump will inflate the bladder until the sensor captures a good and continuous signal from the radial artery. The device will be able to send the data to an app that will record and store it.
The components of our automatic pump applinator are a TR band to apply pressure on the wrist, a TTP ventless pump which pumps air into the TR band, and a disc to apply direct pressure just onto the lids of the sensor. The rest positioning splint is not part of our applinator, but we use it because it helps to get a constant good quality signal by bringing the radial artery to the surface and preventing wrist movements.
For the setting up of the prototype, you guys can see that on the right arm there is a blood pressure monitor, and then on the left arm it is a tear band. The tear band is on top of the wrist, and then there is a splint that will help to bring the radial artery to the surface. There is also a pump, an air pump, which is connected to the tear band, which will allow the tear band to inflate.
For the result of our trial and population, after applying certain amount of pressure to our automatic air pump prototype, it can quell from 10 to 20 minutes high-quality readable signal with nearly constant systolic and diastolic blood pressure reading, regardless the signal drift caused by movement of participants. Also, the pulse pressure is far beyond the 0.1 picofarad requirement we set up before. Furthermore, the heartbeat blood pressure waveform result generated by our system can find out the difference between the blood pressure waveform of each heartbeat in a period of time, and with further research and development of our prototype, we believe that this system has high potential to be used for cardiovascular disease diagnosis.
Prototype has also reduced the signal drift and repeatability pressure. Both participants are the same, participant 31 and participant 44, and they have used the same amount of blood pressure, one 75 and the other 74. You can see that the signal drift for both 9 minutes and the other 40 minutes has reduced to a minimum, and the pulse pressure is also good. We have exceeded the design requirements of the prototype. The pump holds more than 1,000 hours of constant pressure. It does 1 millimeters of mercury per minute and continuously. We also have exceeded the form factor, the user-friendly, the able to accommodate ranges, and time feasibility. As a bonus, we have reduced signal drift, we have repeatability pressure, and we have 40 minutes of good signal.
Although the design team has done a lot this summer, if time had permitted, we would have improved the automatic pump design, tested the prototype to a larger population, captured good blood pressure signal for over 45 minutes, and pursued the kinetic motor design.